so far works nice if we find the data in the cache, but if we don't, then we need to fetch it from memory. And then we also need to select one row in the cache and write the data there. If we can find a row with valid equals false, then it's a good idea to take that. Otherwise, we can take a random row. So let's see what happens. That means if we didn't find it, we use some way to determine which row we should get. And then if the data in the cache is valid, we copy it to memory. This should only be done in reality if the data in the cache was modified, but this is a simple way to explain the basics of a cache. Okay, so we copy it to memory and then we fetch the data from memory. So this can take a lot of time. It doesn't take so much time to send away data from the processor to memory, since the processor doesn't have to wait for it. But when we fetch data from memory and put it in the cache, well, the processor can do something else, but usually it fetches data from memory because some instruction needs that, and usually it will end up with the processor being waiting for this data. Okay, so when we get it, we put the data and the address and set valid to true. Approximately the same thing happens for a store. So if we had this data in the cache already, I mean not the value, but which address it is, then we can just overwrite it and quit. And if not, we will update memory in the same way. I mean, we update memory if the row that we selected was valid, and then we copy the data to the cache. So again, this loop, isn't it slow? No, it's not, because it doesn't exist in the hardware. When we build hardware, we will duplicate this and have one address comparator for each iteration. Okay, so that was that. If we run the factorial program, which computes 5 factorial with the machine.c updated to have a cache like this, then we can count the number of read hits and write hits, and also the number of reads and writes. So this program performs 77 reads and 11 writes. Most of the reads are instruction reads. So what we can see here, all writes, they miss in the cache, and some reads can hit if we increase. I mean, there are read hits also with only 8 rows, but the more rows, I mean the bigger cache we have, the more read hits we get, up to some extent. Okay, and what can this be due to? Well, the writes, they are when we save parameter and return address on the stack. So there are 5 calls to factorial and 1 to main, and that means 11 writes, 2 for each factorial and 1 return address for main, which doesn't have a parameter. So that's the 11 writes, and since they are to new locations on the stack, as we make new function calls, they will all miss. And the reads, Well, the reads are partly to the data that was written, and also instruction reads. And the instruction reads, we cannot get rid of them. I mean the cache misses, because we cannot get rid of all of them, but some could potentially be avoided. Okay. Yeah, that's basically what I said. So some remarks about this cache. It's extremely small, and normally a cache is much larger. Also, there are different levels of caches. The smaller, the closer to the the smallest cache is closest to the processor pipeline, and it's also as fast as the processor pipeline. And then there can be 3 or even more levels of caches, and each one is bigger and slower.